Hi, I'm Ahmet Emir from Middle East Technical University, Turkey, and I'm going to propose a design methodology for primary mirrors of space-borne telescopes as my project. Lightweighting in space studies are important because they directly affect the launch costs. So, as being the heaviest part of a space-borne telescope, primary mirrors lightweight structures are important. I used OptiStruct and Altair Inspire in order to create a new a new pattern of lightweighting for this part. In order to do that, I created an example 360 millimeter Cassegrain primary mirror. It has three regions, as you can see. It has a design region, non-design area, and a fixed area. Design area is where the OptiStruct will essentially work on. Non-design area is the mirror surface, outer circle and inner circle, and fixed area is where I constrain the mirror from. Other than that, we have three different load cases because while producing and testing a primary mirror, the mirror experiences three different loads. They are axial gravity, lateral gravity, and surface pressure. Why do we use surface pressure? Because while polishing the mirror surface, we use a pressurized pad, and that actually has some important effects on quality of the image. Other than these load cases that you can see here also, I implemented an extrusion constraint because we produce the lightweighting structures here by a CNC milling machine, and we want our result to be producible at the end. So an extrusion constraint will guarantee that. Moreover, there is a certain symmetric condition here because I want these three slices of the mirror to be exactly the same. I use the cyclic symmetry condition. When we came to the optimization part, we see that our objective is maximizing stiffness. Overall, image of our quality is dependent on the how surface of the mirror is deformed. In order to decrease that indirectly, there is a more direct way, which is about defining the rest three non-traditional responses. I won't go into that right now. I use maximizing stiffness objective. As the mass target, I choose 30% because in the literature there are experience-based lightweighting studies which can go up to 30%, and we must be competitive with them. We have a frequency constraint too because at the launching environment the mirror is excited with about 100 hertz of excitation. We need our lowest 10 modes to be higher than that. And a thickness constraint is about really the element sizes. It's from experience. So if we run that and later we inspect results, here we see something like this. So this result is logical. Why is it logical? Because the especially axial gravity and polishing pressure create some moments about these constraints. And if you simplify this model and think of it as a cantilever beam under distributed load, if you were to optimize that, you would expect something like thicker at the root and thinner at the edge. And it's exactly like that. We have thicker at the root and thinner at the edge structures. So, moreover, in order to deal with this pressure and its deformations, we have something like a tree-like structure, and that's logical too. However, we have something that we couldn't model here, that is quilting effects. In optics, the image quality is dependent on how a part of the mirror is deformed with respect to others. So if we have total nice less deformation with this case, but the deformation of this part is greater than this part, we will have a problem. So in order to avoid that, usually in literature there are additional walls at here, and lightweighting holes are done these places, and results something like a cell structure. Inspire's functionals are not limited by this. Also, you can just in a couple of seconds have a solid model of your optimization result. It's the polynerves function. Using this, you can immediately see this. This is the solid part. Even if you devote some more into this, you can create better results, but I didn't. So what have I learned from this project? I learned about structural optimization using Altair Inspire as an engineering tool, and applications of optimization in space studies. And one more thing, I learned how to read the results of optimization studies, and I think that's the most important for an optimization engineer. Here are my resources. Thank you for listening.